Let's begin our journey into ionic equilibrium in solutions. Ionic equilibrium is a very important topic. It deals with reactions where ions are present in water and how they reach a state of balance called equilibrium. This includes reactions involving acids, bases, salts, buffers, and even sparingly soluble salts. Now, why is water so important here? Well, water acts as the medium in which all these ions interact. So, whenever we talk about ionic equilibrium, we're mostly thinking about reactions in water or aqueous solutions. Let's study acids, bases, and salts. There are three main concepts that help us understand acids and bases: the Arrhenius concept, the Bronsted-Lowry concept, and the Lewis concept. According to the Arrhenius concept, acids are substances that release H plus ions in water. Bases are substances that release OH minus ions in water. The Bronsted-Lowry concept is a bit more general. It says acids are proton donors. That means they give away H plus ions. Bases are proton acceptors. That means they take in H plus ions. The Lewis concept looks at electron pairs. It says acids are electron pair acceptors. Bases are electron pair donors. Let's go a little deeper into the Arrhenius concept. Arrhenius defined acids as substances that increase the concentration of H plus ions in an aqueous solution, and bases as substances that increase the concentration of OH minus ions. For example, an acid like HX dissolves in water and breaks apart like this. HX aqueous gives H plus aqueous plus X minus aqueous. Or more accurately, HX aqueous plus H2O liquid gives H3O plus aqueous plus X minus aqueous. This shows that the H plus ion actually combines with water to form a hydronium ion, that is H3O plus. For a base like MOH, it dissolves as MOH aqueous, M plus aqueous plus OH minus aqueous. However, there are limitations. This concept only works in water. It cannot explain why substances like ammonia, NH3, behave like bases, even though they don't have OH minus ions. Now, let's explore the Bronsted-Lowry concept. This concept expands the definition. It says acids donate protons, H plus ions, and bases accept them. Let's take an example. NH3 plus H2O gives NH4 plus and OH minus. Here, ammonia accepts a proton from water, so ammonia is a base and water is an acid. The conjugate acid-base pairs here are NH4 plus pairs, NH3, and H2O pairs, OH minus. Another example, HCl plus H2O gives H3O plus plus Cl minus. Here, HCl donates a proton to water, so HCl is the acid and water is the base. The conjugate pairs are HCl pairs, Cl- and H3O plus pairs, H2O. Important point. Each conjugate acid has one more proton than its base. A strong acid has a weak conjugate base and a strong base has a weak conjugate acid. Let's now look at the Lewis concept. According to this theory, a Lewis acid is a substance that accepts an electron pair. A Lewis base is a substance that donates an electron pair. For example, BF3 is a Lewis acid because it accepts a lone pair. NH3 is a Lewis base because it donates a lone pair. Let's understand this with a reaction. BF3 plus NH3 gives BF3 and NH3, which form one compound. In this example, even though BF3 doesn't have any protons, it still behaves as an acid by accepting electrons from ammonia. So in short, electron-deficient molecules like BF3 and AlCl3 are Lewis acids. Molecules with lone pairs like NH3 and H2O are Lewis bases. Next, let's learn about the ionization of acids and bases. In water, acids and bases ionize. That means they break apart into ions. This gives us either H3O plus ions or OH minus ions. Strong acids like HCl, HNO3, and H2SO4 ionize completely in water. That means they give away all their protons. Strong bases like NaOH and KOH also dissociate completely to produce OH- ions. On the other hand, weak acids and bases do not completely ionize. Only a small portion of their molecules split into ions. Most of them stay in the original form. This behavior can also be explained using the Bronsted-Lowry concept. Strong acids donate protons easily, and strong bases accept them easily. In acid-base equilibrium, protons are transferred in both directions. If one acid is stronger than another, it pushes the reaction to favor the formation of weaker acids and bases. Strong acids form weak conjugate bases. Weak acids form strong conjugate bases. We also use indicators like phenolphthalein and bromothymol blue, which are weak acids that change color when they ionize. These indicators help us track pH during titrations. Let's now study the ionization of water and the ionic product of water. Water itself can undergo ionization. This means a very small number of water molecules split into hydrogen ions and hydroxide ions. H2O on ionization gives H plus and OH minus. Or more precisely, 2H2O gives H3O plus and OH minus. At 25 degrees Celsius or 298 Kelvin, the product of these ion concentrations is a constant known as the ionic product of water, represented as Kw. So, Kw is equal to concentration of H plus multiplied by concentration of OH minus ions, which in turn gives 10 raised to power minus 14. Taking the negative logarithm, pKw is equal to minus log Kw is equal to 14. Also, pH plus POH is equal to 14. In pure water, the concentration of H plus is equal to the concentration of OH minus. Both are concentration of H plus equals to concentration of OH minus is equal to 10 raised to power minus 7 molar. So, pH is equal to minus log 1 times 10 raised to power minus 7 is equal to 7. That's why pure water is said to be neutral, having a pH of 7. We hope that you have understood the topic. You can now study chapter notes, watch video lectures, and solve MCQ tests of this chapter on EduRev to ensure you score well in your exams. And that's not all. You also get amazing courses for maths, science, English, Hindi, and much more for NEET. Thank you.